So before we head to the next feature, let's do a quick recap. The first point is that we are going to use a NoSQL database with the text data type for content. The second point is that we're going to be using version history through cron jobs. Cron jobs will be calculating what is the current version of this document after every few minutes. So that is 30 minutes per cron job. But we also talked about reducing the peak load by actually splitting our cron jobs into 30 pieces and then finding hash buckets for every document. The next point is that we are going to be using compression to keep the document sizes small. And also we are going to be using file storage for archived documents. So that's going to bring the cost down. Then we are also having a log of operations. Whenever requests come in to add or remove or whatever changes you want in a document, we are going to be maintaining that log for a while so that there are faster writes into the log. And whenever you're serving reads, what you're doing is you're reading the log which is still not processed, performing those operations on the document and then serving the response to the client. Now comes the fifth point, which is concurrent writes. The important point here is that this concurrent means two people around the world making changes to the same document. So for example, if I have a document over here with the contents ABC, I have two people. One is user A who's in the US and user B who's in India. Okay, and they both make changes. So user A, let's say, says add D to the end of the document. So the version that they are looking for is A, B, C, D. This is their expectation. The Indian user locally makes a change where they delete B. So the version that they should be able to see is A, C. They are sending this command of delete B. So eventually what should happen to the document is that these two operations should be taken together, and add D and delete B, the resultant document should be A, C, D. Okay, but the problem is these operations might reach in any order, and you have to make sure that after a certain period of time, we are not sure when, it might be eventually consistent, but it has to be consistent. Like both the users have to be served this document of ACD so that they're aware of these two changes that have been made. How do we go about this? The first approach, the simplest approach, is to take locks on the documents. So whenever a person says, I want to change this document, so let's say document ID is 123, contents is ABC. So please take a lock on document ID 123. Okay, I took a lock. The first operation, let's say, is add D. So 123 has a lock, write lock on ABC as the content and add D as an operation. At the same time, the Indian user tries to delete B, but they are blocked on this lock. So delete B tries to acquire a lock on 123, fails to acquire that lock and has to wait till add D completes. So when that happens, you have 123 changing to A, B, C, D. Finally, this operation gets this document because this lock is then released. Once it acquires this lock, it makes the change and you have 123 and ACD. Okay, this is a simplistic way of thinking because you're not going to be removing a single character or adding a single character all the time. You might take all of these characters and make them bold. Okay, that might be a complex operation. You might say that remove this entire sentence while this person says please add D to the end of the sentence. So this approach does not do very well. This is called pessimistic locking, or you can just say you're taking a exclusive lock. Okay, that's a write lock, and because there's a lot of writes, if you're taking exclusive locks on the entire document, what's going to happen is there won't be concurrent writes. Like you're basically getting rid of concurrent writes by taking locks. So that is too slow though, and we want people to make changes concurrently. This approach causes too much contention and is too slow. The other approach, which is very similar to this, is called optimistic locking. It's slightly worse, honestly, because what's happening here in an optimistic lock, what happens is you have the command add D to ABC and then it goes ahead and makes this change ABCD. Delete B does not wait for this lock to be released. What it does is it assumes that ABC is not locked. So it takes ABC, performs the operation delete B on it to AC. This is the document copy it has. Add D also has a document copy ABCD. Okay, so these are the two document copies. Now one of the writers is actually going to win. So they both try to write to the memory location of 123, this document 123, and one of them will win. So if you have AC over here, the person who did not win, ABCD, the person who did not win is actually going to be cancelling their operation first. So this is first deleted. It then either retries or entirely fails the operation. So if you do a retry on AC at D, you get ACD. Okay, in this particular case, it's working. But like I said, it can be much more complex, these operations. However, even if you do pass, there's a lot of wasteful processing that is happening. To take a copy of this entire document through an optimistic lock is not a great idea either. So we are seeing that optimistic locking has a problem of taking the entire copy of the document, which is very expensive, plus it has wasteful processing. Pessimistic locking, the standard type of locking, is also very wasteful because multiple writers can't write at the same time. So maybe locking itself is not going to work for us. Okay, so locks are not going to work for us. Instead, we need a specific algorithm which solves concurrent writes. So the way we are going to go about this is actually creating two copies of documents, like ABC, let's say, is the document. You perform an operation at D that splits this document into another copy of ABCD and one copy of AC, okay, from the Indian user of delete B. This is just conceptual. It's not going to happen. It's not going to make an entire copy, but conceptually this is what is happening. Basically, there are two operations that you have. So ABC with delete B and ABC with add D are the two copies of the document that you have. Eventually, these two documents have to merge into a single document where ABC, add D and del B go through. Okay, so what we are doing is, you might have multiple clients, 30 clients, 15 clients, all of them take documents and then eventually they merge the operations that they have instead of trying to merge the state. Okay, so if you try to merge operations like this, then it's a feasible problem. Over here, you're seeing that this is actually very similar to the log operations that we had, so that we can give writes are faster. That concept can be added over here, but there's a slight problem here. Firstly, how do you order the operations? In this particular example, adding D and deleting B can be done in any order. You're going to get the same result in the end. But in certain cases, as we'll see soon, you will have a problem with the ordering of the operations. The second problem is that who's going to define how to actually perform these operations? We are seeing add del as simple operations. Like we said, they can be complex bolding operations, or you want to underline certain text, you want to hyperlink certain text. That's not very easy. So there are two approaches to solve this kind of a problem, and we'll be going through briefly over them, because in a typical interview, you're not going to be actually asked this in detail, but still we'll just go through it so that we have a good idea of what's going on underneath.